Welcome to Physics 10 and this first lecture video in the series of 30 lectures for Introduction to Physics, a conceptual physics course. We will spend this semester and the next 30 lecture videos, about 1 to 2 hours length each, learning about all the topics of physics, from mechanics to classical physics and to modern physics, including special relativity and quantum mechanics. In this first lecture video in the series, we are going to look at the first chapter, chapter 0 of the textbook, setting the scene for the realm of physics we will cover in coming weeks. We go into some detail talking about the language and hierarchy we use when we refer to scientific ideas, with some emphasis and illustration of what we mean by a scientific model. And you will find that we physicists, of all the scientists, place a heavy emphasis on physical units and how they are fundamentally related to the three basic units of length, mass, and time. And you will see the connection between these basic fundamental units and derived units in Intro to Physical Units lecture. We follow this with some examples of unit conversion exercises, along with an online tool that you can use for unit conversion after you feel like you had enough practice converting units by hand. Finally, this video series is being put together in the year 2025. You have seen AI, artificial intelligence, and in particular generative AI like ChatGPT in the news, and you may even have used these tools yourself. So, I'll talk about generative AI and the potential role they may play in your learning of physics. I'll share some ways in which I have utilized AI and plan to use AI for this class. We'll start with a Chapter 0 overview shortly. I'm excited for the upcoming weeks when we will touch on all the important ideas of physics. Hi, welcome to Physics 10 Introduction to Physics. In this video, I want you to give an overview of Chapter 0, our first chapter. It's numbered Chapter 0 because it's a little bit outside of our unit structure. The class is structured so that in the first two units, first half of the class, we cover mechanics. And we will use these mechanical concepts and tools to talk about laws of classical physics and laws of modern physics. And our first chapter is in the introduction, before Unit 1. So it's numbered Chapter 0. It's got 3 short sections talking about realm of science and physics, and a little bit of introduction about physics, and discussion of physical quantities and units. So, in the chapter, you will see discussed defining physics and science, just talking in broad strokes about science, our theories and laws of a mechanical universe, physics realm or the mechanical universe, and the scientific method that you hopefully have seen in middle school, high school. If you haven't, you will see it described in the chapter. It's an iterative process that consists of a number of steps that can vary a little bit. But the main thing is, the important part is the experimental testing. That's what separates the scientific method from frankly, myth-telling and other non-scientific ways of studying things. And within science, we have different hierarchy of, I guess, what we think we know in science. There are things that we call laws or principles. These describe some generalized pattern in nature. And sometimes the law and principle are interchangeable. Law can cover a fairly wide-ranging number of things of different reliability and generalized applicability. So watch out for the context. I think when it comes to theory and model, we are more precise about the language that we use. When we talk about theory, it'll often be about things that theory, it'll have a whole structure to it. This is what it means, more complex and dynamic than a law. And when we talk about model, it's often centered around calculation. Model is a way we can compare our theories to an experimental evidence. So a model gives a way to calculate things that can be compared to experimental results. And sometimes a model will be used to represent things that are frankly difficult to visualize. I give an example of model in a separate lecture video using atomic models as an example. So watch out for that. There's a more detailed, longer lecture video coming up. And in this chapter 0, we also talk about some of the things that will be coming up, division of physics. The physics is divided into, I guess, classical and modern physics. After we cover mechanics in units 1 and 2, you will see us cover laws of classical physics. And really, the classical physics culminates with the study of light that comes out of a study of electromagnetism. And it's really fascinating to me how much of the beginning of modern physics comes from light. Relativity, its beginning is from when Einstein was thinking about properties of light and how light emitted or transmitted from moving body would behave. In thinking about that, he came up with the relativity, which we'll get to in Unit 4. And also, when it comes to quantum mechanics, study of light, again, gives one of the beginning points of quantum mechanics in photoelectric effect. And that leads to other things like atomic theory and all that. And a good chunk of beginning of quantum mechanics has to do with how light interacts with the matter. So that's a brief preview of some of the things you will see in the next 15, 16 weeks. And let me get to the one last thing that we'll cover in some quantitative detail this week. That's about physical quantities and units, specifically the SI unit system. With the units, I think the one thing that I would highlight is just the amazing way physical quantities are handled in physics. In physics, really, we only need 3 fundamental quantities of length, mass, and time. In the SI unit system, these are in meters, kilograms, and seconds. And now in SI unit system, we also define an electric unit that's fundamentally defined to be the electric current in ampere. But this is a choice that's made in the SI unit system. There are other unit systems that only uses length, mass, and time. All other physical quantities can be derived in terms of these fundamental 3 quantities. And that's what derived units talk about. I have a lecture video that I'm borrowing from my Physics 4A lecture that gives an example of a pressure as a derived unit that can be described in terms of length, mass, and time. The chapter also talks a little bit about advantage of metric system, and I guess it comes down to the metric prefixes that gives a different power of 10 scale, the kilo, milli, nano, the standardized prefixes. I hope you will memorize some of them if you haven't already memorized. But the physics being fundamental science, we are not big on memorization. I just want you to know some of the really common ones, like a kilo, milli, mega. The chapter has a whole table of them, and you might want to mark that as a reference for you to come back to as you work through this course. Yeah, and this is the one advantage of a metric system compared to the customary or imperial system of units. And finally, unit conversion is something that I want people to learn how to do. I have some examples of lecture videos, and the textbook has some examples of unit conversions. Please take a look at them. You'll have some homework questions. So So that's the overview of this chapter, our chapter 0. I went into a little more detail than I normally would in the future chapter overview videos because this is a short chapter. In the future videos, I'll try to keep this brief and stick to summaries because you will have lecture videos that'll flesh out the details in the chapter in greater detail. Hi. In this video, we will distinguish between models, theories, and laws. The textbook does address this distinction. A model is a representation of something that is often too difficult to display directly. A theory is an explanation for patterns in nature. And a law uses concise language to describe a generalized pattern. Now, what do these words mean? To make these distinctions clear, we really need a concrete example. So, for this example, we go to the models of the hydrogen atom. This is a PHYT, PHET simulation called Models of the Hydrogen Atom. So, you probably have heard of an atom before. There have been many versions of atomic theory, dating from the time of ancient Greeks. Now, no one has ever seen an atom in an experiment, which is what this simulation is illustrating. You have a vapor cell of hydrogen gas, which is invisible. You send in some light and observe how this light interacts with this invisible hydrogen gas. You've seen some light particles reflect off. An atomic theory starts out with the model of the hydrogen atom, which is what the scientist believes what the atom is really like. The billiard ball model would say that a hydrogen atom is like a hard shell sphere, like a billiard ball. This would be closest to the Greek conception of an atom. And we know this model is wrong because when you send in light, you expect them all to bounce off. And from the experiments with the real hydrogen atoms, we know it doesn't work that way. So in the modern era, starting around 1900s or so, people had different ideas about the hydrogen atom. Let me turn this slide off, it's kind of getting annoying. So there was the plum pudding model, which was still wrong. And there was the classical solar system model. What happened there? And later in the semester, we are going to talk about the Bohr model. Theories and laws play some roles in the construction of a model. Take the plum pudding model, for example. This came out of discovery of the electron, which is an electrically charged particle that would pop out of atoms. So people thought, we will talk about electricity in more detail later in the semester. This electron could be bound to the rest of the atom if the rest of the atom was positively charged. This red pudding thing represents that positively charged part of the atom. This was the model they constructed, which was consistent with the theory of electricity, which was very well developed at the time. But then, people did more experiments and discovered that atoms had a very tightly packed nucleus. The positively charged part of the atom couldn't be spread out like this. So theorists got to thinking more about what other model would fit the known facts better. They took an inspiration from the solar system, which has discrete objects that are attracted to each other by gravity, and thought maybe atom could be like that. They are attracted, but they orbit each other, so it doesn't fall in. Let me pause and run the simulation more slowly. Now, what's going on here? This was the result of physicists applying the existing theories and laws to this solar system model of hydrogen atom. We will get to this later in the semester, but the well-developed theory of electricity and magnetism, we call it electromagnetism, said that an electrical charge moving in a circle radiated away a wave which will carry away energy. Then the law of conservation of energy said that the electron must be losing that energy, which causes it to spiral in and kaboom, collapse onto the proton, like a satellite falling to Earth when it loses orbit. Now, we don't see hydrogen atoms imploding all around us, so this model can't be right either. Either the model is wrong, or the laws and theories we believe in are wrong. And in the hierarchy of things, the smart money is usually on the laws and theories, which stood the test of time and numerous experiments being correct, and new models not quite being right. Even though the solar system model is wrong, it was a very useful model because it forced the physicists to think outside the box and discover an entirely new area of physics that we now call quantum mechanics. The Bohr model is the first of these quantum mechanical models. Bohr kept all the known laws, theories, and facts. The Bohr model still has a positively charged nucleus, proton, and it assumes the law of conservation of energy. And it assumes that theory of electromagnetism is still correct for the most part. Bohr added one more guess. Let's call it principle of quantization to build this model. His guess was that these orbits had to come in discrete levels. So the electron couldn't gradually spiral in like it did in the classical model. Now, not every pioneering guesses by theoretical physicists are right. They come up with these fun ideas, one every week. Most of them are wrong. But Bohr's guess turned out to be right. So we now teach this model in our physics classes. By the end of the semester, we will barely touch on this Bohr model, but even this Bohr model isn't quite right. You see two more models here, de Broglie model and Schrödinger model. The Schrödinger atomic model is what we now believe to be the completely correct model of hydrogen atom, down to the last detail. But you see that we lost something here in the pursuit of correctness. Let's call it clarity. Except for those of you who took chemistry with electron cloud, orbitals, and all that stuff, this picture probably doesn't make a lot of intuitive sense. This is a trade-off we often need to consider. The trade-off between ease of understanding and accuracy. We will definitely discuss the Bohr model by the end of the semester. I think it's intuitive enough without a lot of math, especially if we have a little bit of time to spend on it. And we'll possibly even go into a little bit into de Broglie model, which hints at the weirdnesses of quantum mechanics. But we won't cover the Schrödinger model because to get something from this model, you need to know something about differential equations that's covered in classes that you take after calculus. So I hope this example of atomic model made the distinction between models, theories, and laws clearer. These are words that even we scientists sometimes use sloppily interchangeably. But there are times when it is important to draw this distinction. For example, to dismiss a new idea that you don't like, you shouldn't really say, that's just a theory. You should instead say, that's just a model. Well, or not. Bye. Hi, in this video, I'm going to talk about units. I think a lot of people have seen units in previous science class, or you have some basic idea that when you're counting physical quantities, there's some reference size of thing that you use to count things. So I think that's the way in which you have seen units, and I think as far as um, intuitive idea of unit goes, that's good. You know what inches are, you know what centimeters are, and what I want you to go a little bit deeper is the importance of units in physics. As you might know, physics is the fundamental science, and we have a very particular way we handle units that might be different from how you have seen units handled in biology or even chemistry classes. So your textbook, I mean, section 1.2, it gives these SI base units. And what I really want you to focus on are these first three. These are really the fundamental units. And it's actually amazing that of all the physical quantities that you can measure in the world, you can boil them down to these three. Let me copy this into a note so that I can talk about it in more depth. So this is the claim I'm making that I want you to pay attention to. In chapter 1 of our general physics, we are introducing these three units: length, mass, and time, in meters, kilogram, and seconds that you might be familiar with already. And the claim I'm making is that in physics, these three units are really all the units that we need. I want to draw a contrast. Think about, for example, unit of pressure. I think this is a unit that you might have seen in chemistry. So if I'm trying to think back to my chemistry class, I think I remember learning about this. I learned about a unit of atmosphere, which can be expressed in unit of torr, which is somehow equivalent to millimeters of mercury. And I think there was one more, kilopascal, 101.3 kilopascal. I may be misremembering it. You should look it up to be sure. Um, so this might describe the, I don't know, chemistry approach to units. So to talk about one quantity, pressure, you've heard quite a few units: atmosphere, torr, and pascal. And maybe you don't need all of them. And I guess chemistry is a fundamental science. So what? Uh, so the so the way of representation that a chemist emphasizes values will be different from how we physicists like to emphasize and represent. And to draw contrast, in physics, we prefer not to introduce any new units, and in some fundamental sense, we don't. I mean, we do use unit of Pascal. That's the most preferred unit in physics to describe pressure. But how we describe this Pascal is in terms of length, mass, and time. And this is how you will see us do it. So if we have quantity of pressure, pressure is actually related to other physical quantities. It's related to force, and it's related to area. Pressure is a force per area. I think we covered that towards the end of the semester. And I think you know enough geometry to know that area can be represented as product of two lengths, length times another length. But you might look at force and say, oh, so force is a quantity that we would maybe need a new unit to express it in. And it's the amazing thing that you learn in physics, that force can actually be expressed in terms of these three basic quantities. So in a couple of weeks, you are going to learn about Newton's second law, which says that net force is equal to mass times acceleration. So mass is one of the quantities that we already have a unit for, kilogram, and acceleration is another quantity that we can express in terms of length and time. So we'll cover it in the coming week. acceleration is, oh, how do I say this without calculus? I'll just say change of position per change of time, which is velocity, per change of time. So all of this put together, I guess if you are just interested in the quantity, the unit of acceleration, what we would say is the unit of acceleration is unit of length. That's the same unit as unit of position per unit of time squared. So to wrap it all up, to describe the unit of pressure, we can describe it as this combination of length, mass, and time units. The combination is, so one factor of mass in the force times, so I have acceleration, so one factor of length. And in the acceleration, we have two factors of time dividing, time squared. So that's a unit for the force divided by area. So that would be two factors of length. So length squared. So that's a unit of pressure in terms of the fundamental units of mass, length, and time. Now, we are going to be working with SI unit system quite a bit. I think it stands for System International. It's some French, or it means international system. So in the SI unit system, it's constructed in a very peculiar way. That peculiar way is that whenever you have derived units, so for example, pressure comes in unit of Pascal, and Pascal is one of the derived units. Derived units are constructed from these fundamental units by simple multiplication. So I can say 1 Pascal is equal to 1 kilogram times meter per second squared, also per meter squared. Oh, so if I simplify it a little bit, canceling out this, I can say 1 Pascal is 1 kilogram per second squared per meter. And within the SI unit system, we deliberately constructed these derived units so that we don't have to worry about what this factor will be. It'll always be 1. And this is a contrast to more customary unit system where one atmosphere, how that relates to other basic units, you have to memorize it. Same deal with the torr and millimeters of mercury. So the main reason for having the SI unit system is to make this derivation process simple. So that as long as you know how these physical quantities relate to each other, from knowing this, you already know how the units will relate to each other. So your textbook spends some time covering these basic units of time, length, and mass. It's interesting history. I recommend that you read through it. And I guess we don't have time to quite talk about it in depth. But one thing I want you to put it on your radar is something called dimensional analysis. Let me spell it out. And you will see examples of this throughout the semester. I guess at this point, I will just say this much. It's a way of validating your mathematical expressions by taking careful look at the units that your physical quantities are expressed in. So you might call it analysis of units. And it's a very powerful tool that whose importance you will recognize more as you go into higher levels of engineering and physics. So I'll leave that there. Thank you for watching. Until next time, bye. Hi. In this video, we'll work out a few examples of unit conversion calculation. Before we start, there are some examples of unit conversion calculation done in the textbook. It's in section 1.2 physical quantities and units under unit conversion and dimensional analysis. So please do take a look at it. This video is meant to supplement what is already in the textbook. Alright, let's get started. So we are going to work out three different examples. The first example will be length conversion. For the second example, we will finish up example 1.1 that's in the textbook. Well, by finish, I mean there was a calculation that I wish they did, but they didn't, so I'm gonna do it. For the third example, we are going to do conversion of miles per hour to meters per second. This will be very useful in general because most of us have our intuitive sense of speed based on miles per hour. But in SI units, meters per second is the SI unit of speed. So we need to start building up intuition for how fast is just too fast. All right, let's get started. First, with the length conversion. Let me do a fairly useful example of length scale. So if we think about how high is the atmosphere, the typical number that we can throw around that you will see later on in the semester is the atmospheric height of about 10 kilometers or so. The actual atmosphere actually extends much above that, but at some point the air gets so thin that I'm just compressing it all down to 10 kilometers. So if the atmospheric height is 10 kilometers, well, in the customary units or English or imperial units, what is 10 kilometers? So the question is, what is the 10 kilometers in, let's say, miles or in feet? Those are the two fairly large length scales that we should be able to convert this into. So we start out with the number 10 kilometers. And what we now need is a conversion factor. What a conversion factor is, it's essentially number 1, but you write it in a very specific way to convert one unit into the other. So for example, we are starting out with a unit of kilometers. So we want to convert it to miles. So the conversion factor that we are going to build, it's going to have kilometers in the denominator. This makes it so that after we do all the calculation, the kilometers will cancel out. But you can't just divide things by a new number without changing things. That's what the numerator is for. We are going to put in a physical quantity there that is equal to 1 kilometer. So that all we did was we multiplied by a factor 1. So we didn't change anything. All we changed was unit. Now this is where I need to look up the conversion factor. Fortunately, your textbook has these conversion factors at the very end under useful information. This is like a back of a physical textbook. And when you scroll down, you will see a section for SI units. And that's where I see these factors relating inches to centimeter, foot to meter, and mile to kilometer. So I see that the conversion factor I have doesn't have 1 kilometer, so I'll need to change a little bit what I write. So, but what I can say is 1 mile is equal to 1.609 kilometer. So if I write this fraction, I'll be just multiplying by 1. So the fraction is 1 mile per 1.609 kilometer. And as our goal was, kilometers cancel out, only mile remains. So the final number we get will be in units of mile. Now I can't really do the 10 divided by 1.609 in my head. So I'll use a calculator. So 10 divided by 1.609. All right, 6.22. With the significant figures, I will say this. In this class, if you keep 3 significant figures most of the time, you'll be fine. If you want to be extra careful, you can keep 4 significant figures. But more than that is really unnecessary. So here, I'm going to keep 3. So 6.22 is what I want. So 6.22 miles is the atmospheric height in miles. All right, let's go through the second part more quickly. We want the answer in feet. So we start out with the same number, 10 kilometers. And I remember from looking at the useful information earlier that I'm not given kilometers to feet conversion. So I am given feet to meter conversion. So what I'm going to need to do is I'm going to have to convert twice. I will need 2 factors of conversion factors to get my final answer in terms of feet. The first factor is easy. I need to convert kilometer to meters. And this is really why we use SI units in sciences. It's really easy to convert from larger length to a shorter length. Kilo means 1,000. So 1 kilometer is 1,000 meters. I don't have to look up anything to know that. Once you have the prefixes memorized, then you have this memorized. All right, I don't actually remember what the meter to feet conversion was. So let me look back at the useful information. All right, so the meter to feet conversion is 1 foot per 0.3048 meters. So 1 foot per 0.3048 meters. Then you see that all the units we don't want cancel out. Kilometer cancels out kilometer, meter cancels out meter. So we are only left with the feet, which is the unit we wanted. So I still can't do this in my head, so I will use calculator. 10 multiplied by 1,000 divided by 0.3048. 32,808. So keeping 3 significant figures, this would be 32,800 feet. That's it. That's the first example, converting length between an SI unit to English customary or imperial unit. All right, let's move on to the second case. We want you to finish example 1.1. So example 1.1 has, suppose you drive 10 kilometers in 20 minutes. What is the speed in kilometers per hour and meters per second? What I noticed was missing was there's no miles per hour. That's the speed a lot of us are familiar with, so we should really have that. So let me do part C, calculating this average speed in miles per hour. So the part C to example 1.1 that I'm adding is calculating 10 kilometers per 20 minutes in miles per hour. So we go through this same as last time. So we have our number, 10 kilometers per 20 minutes, and we are going to multiply by conversion factors. We have 2 units that we are trying to get rid of, kilometers and minutes. So we are going to need 2 conversion factors. Each of them are factors of 1 that's designed to cancel out the unit we don't want and retain the unit that we do want. Let's get rid of minute first. That's the easier one. So I want to cancel out minutes. So on the numerator, I need the minutes on top. I want to convert it to hour. So on the denominator, I need hour here. And here, I'm just thinking about, okay, how many hours is equal to how many minutes? Well, there are 60 minutes in 1 hour. So that's our first conversion factor that will get rid of unit of minutes and give us the unit of hour that we want. For the second factor, I have to look up the number again because I never have this memorized. So going back to useful information, I want kilometers to mile conversion. So 1 mile is 1.609 kilometers. So 1 mile is equal to 1.609 kilometer. Making sure we put them in the correct places so that this kilometer in the numerator will be cancelled out by this kilometer in the denominator and we'll be left with a mile. So the unit that we are left with is miles per hour, or mph. For the numbers I have to use calculator again. So it's 10 divided by 20 multiplied by 60 divided by 1.609, and that's equal to 18.6 miles per hour. Alright, that was easy enough. Now let me move on to the third example. So we want to convert a number in miles per hour to meters per second. Let me come up with a number that's going to be familiar to you. So if you're driving around in a residential neighborhood, then a typical speed limit might be 30 miles per hour. So let's convert 30 miles per hour to whatever it is in meters per second. And this will also give you some useful, quick way to convert from miles per hour to meters per second. It's actually fairly easy once you know the numbers. So we are converting 30 miles per hour to meters per second. So it looks like we will need two conversion factors again. Miles to meters and hour to seconds. Let me do hour to seconds first. That's the easier one. So I have 1 hour on the numerator, and on the denominator I want seconds. So it's a question of how many seconds in an hour. If you have it memorized as 3600, great, good for you. If not, this is the consideration you have to go through. Okay, how many seconds in a minute? Well, 60 seconds in a minute. How many minutes in an hour? 60 minutes in an hour. So the number of seconds is going to be 60 times 60 seconds. And I can just do that in the calculator later. Alright. And I need miles to meter conversion, which once again I never have memorized, so I'll need to look it up. So under useful information, 1 mile is 1.609 kilometers, or in meters it'll be 1,609 meters. So let me write that. So miles on the denominator to cancel out miles on the numerator, meters on top to get meters. So 1 mile is equal to 1,609 meters. Good. So you can see that all the units that we don't want cancel out. Hour cancels out, miles cancels out. We are left with meters per second, and we bring our calculator to finish this calculation. 30 divided by 60, and because of the way this calculator works, I just have to divide again by 60 and then multiply by 1609. So I get a number of 13 or 13.4 meters per second. 13.4. So this is a fairly accurate, exact conversion. 30 miles per hour is a 13.4 meters per second. Now, there's a kind of quicker way to do this calculation so that you can do it in your head. So this 13.4, it's very close to 15. Now, if it were 15, then we would be saying 30 miles per hour to 15 meters per second. It's a simple division by 2. So if we just simply want you to get a quick sense of how does a number in meters per second relates to a number in miles per hour, it's a simple factor of 2. So you take the number in miles per hour, divide it by 2, that'll give you a number in meters per second. So if you are speeding at 100 miles per hour, then you're moving at approximately 50 meters per second. So that's the last of the examples I want you to look at. Let me point out one free tool that you have access to that's going to help out with the homework. I guess I leave it up to your judgment how often to use it, but it's good to have around as a way to check your answers. So let me show it to you. This tool is something called Wolfram Alpha. You can access it by going to www.wolframalpha.com. It's a free resource. There are some features that you can only access with a pro account, but I don't think we do anything in this class that you really need it for. This search engine is aware of units. So you can have it actually do the conversion for you. So let's take the first example. 10 kilometers in miles. Well, 6.137 miles. Or in feet, 32,800 feet. Or the other example, 10 kilometer per 20 minutes in miles per hour. I might have to hit enter for this one. Let's try that. So it tells you how it understood your request to make sure this looks correct. Then if this looks correct, then this answer ought to be right, 18.6 miles per hour. And if you go back in the video, you will see that's what we calculated. And finally, well, let's try the 100 miles per hour in meters per second. 100 miles per hour in meters per second is about 45 or close enough to 50 meters per second. So this is a very useful tool. Now, it's a question of, I do want you to know how to convert some units. So this is like long division. So people teach you long division in middle school, elementary school, high school, even though you are most often going to use calculator because there's a value in knowing how it's done if you didn't have these advanced tools. Wolfram Alpha is the same thing. So if you just need the answer, you can use this to get the answer. But I strongly encourage you to learn how to do this by hand and use this tool to just double check your answers. So that's all the examples I have. I guess please get started on the homework early. And if any questions come up, please contact me. I'm happy to answer any questions you have. Bye. Hi. I thought I would record this video talking about a new-ish kind of issue that's come up since the time I recorded most of the lecture videos that you will see in this class. I am talking about AI and learning physics. So most of the lecture videos that you will see in this class, they were recorded some years ago. Some of them go all the way back to 2018. Some of them are more recent, maybe 2021. But most of them were recorded before the AI came onto scene. I guess ChatGPT first came out in late 2022, and it was really in the news starting in 2023. I think I was starting to see it in classrooms in 2023. So I thought I would record this video addressing generative AI and its role in your learning physics. And let me start by saying I am just impressed with the progress of AI over the last couple years. When it first came out, I probably would have said, and I did say, oh, this is a B- level response. It gets some things right. The writing looks really polished, but fundamentally it's wrong in important places. It was making mistakes with the Newton's third law. Whenever you asked it kind of modern physics questions, it made the mistakes that I would say was typical of a B- student. And I think I stopped saying that like last year. And this year, yeah, I definitely would not say generative AI, ChatGPT gives you the kind of the responses that are typical of a B minus student. It's probably at an A student level response. And at first, you could distinguish between an AI response and a human response based on, I guess I would say, modal capability, in the sense that, so us human beings, we can write, we can draw diagrams. They are kind of the tasks that you've learned to do in school, and it sort of comes to us natural intelligence beings naturally. But the large language models, they are language models. And frankly, ChatGPT, even until recently, couldn't draw accurate diagrams. So until recently, I would have said, if I want you to make sure written work went through some sort of human brain processing, I would have said, draw a diagram. But I will say, having looked at the most recent release of Google Nano Banana Plus 3 or 3 Plus, yeah, I don't think even that's gonna hold anymore. There will be written work that's completed with beautiful drawings, natural looking, and it might be fully AI generated. And I think I heard this saying in a podcast, and when I heard it first, it stuck with me. That it goes something like, the generative AI that you see today is the worst AI it's ever gonna be. It's improving so quickly, and even if worst case scenario for people working in AI, the progress stopped cold today, nothing new ever got released. Well, the models that you see out now, it's not like us biological beings that grow old and die. These computer programs, they're gonna be around forever, or as long as the companies are around. So the kind of generative AI types, capability, ability that you see today, that's gonna be around forever. That's the worst that you will see AI be. And I think we all have seen impressive year-over-year improvements in AI. And like a lot of new technologies, there will be kind of rapid progress, and then it'll plateau at some point. And when it plateaus, it'll be at a greater level of capability than what we see today. So with all of that in mind, that's why I want you to record this video, include it into the lecture videos I'm putting together right now in year 2025. It's a collection that will be composed of many videos that were recorded before AI, but where it's appropriate, I will record a new video like this, reflecting the full capability of technology that's accessible to me and to you. So in this video, I want you to share some of the ways I've been keeping tabs on the AI capability, and share some of the ways I use AI in my work as your instructor, mostly, and how you might use AI if you use it at all. So first, let me start by sharing how I've been keeping track of AI. So this is our YouTube channel, COA Physics YouTube channel. This is the handle. There are links in a bunch of different places. You can see my past record of kind of keeping track with AI. So as I said, generative AI first broke into the scene late 2022, early 2023. So some of my earliest playing with the generative AI, I think it's old enough that it doesn't feature on the homepage anymore. You have to kind of go to one of the old playlists dealing with the conceptual questions, and yeah, I think it's here. So some of these actually predate AI. I was making these videos as a can respond to a student request. Which we used to have something called the conceptual questions that you probably won't see in your class anymore. I'm gonna be taking out those assignments, but we had them, and these are just me commenting without AI. And I thought in the spring of 2023, when ChatGPT first came out, I thought, that this is interesting. And I think I was beginning to see AI generated answers, or answers that I suspected were AI generated. And I was thinking, all right, how well does AI, ChatGPT, do on these questions? And I will say initial results were, mixed. Like many of the questions where you could answer in an essay type answer, it did pretty well. Sometimes it would hallucinate, but the kind of the physics, the basic physics we teach, it would do mostly okay. Now, when it gets to special relativity, like relativistic paradoxes or particle physics, it would then start to struggle. And now, one capability it took a long time for AI to get was drawing diagrams. So I think this one I did with the perplexity. And let me see if there's one I did with a relatively recent version of ChatGPT from last year. Not the most recent one, but still last year. So yeah, this was when I was first trying it out with the ChatGPT for. I used the Perplexity for a semester, a year, and then I switched it over to ChatGPT because with the release of ChatGPT 4.0, I think it was getting to be really capable. So, but these early days, it wasn't really doing. So there are some things that doing all that well. And if you look at this video, you will kind of see that it doesn't actually generate good free body diagrams. And here, so this was year and a half ago, spring 2024. It was crashing all the time, and now it would always generate a good description of the free body diagram. But when you insist on a diagram, sometimes it'll try to do it through programming, and this was all garbage. Not the case anymore. I think with the ChatGPT, it's still sometimes hit or miss. Sometimes it doesn't draw correct diagram. But Google Nano Banana has been a lot better. But this is one of the ways I've been keeping track of AI capability. And at some point, I actually took conceptual questions out of the assignment set. I got frustrated with how many students were basically submitting AI answers. And this was a peer graded assignment, and I think a lot of aspects of it, there were more downsides to it than what I thought was the students learning from the assignment. So spring 2024, that's sort of the last of these me keeping track of how well does AI do, because starting with the fall 2024, I wasn't asking these conceptual questions anymore. And another way in which I'm keeping track of AI capability that's still ongoing, so it's on the homepage, it's what I'm calling problem solving with ChatGPT. This playlist is ordered in a reverse chronological order. So the top video is the most recent one. This is actually from, I think, posted one day ago yesterday. And this is from the virtual class session I did for Physics 4B in last week, kind of wrapping up thermodynamics. And here it's AI solving fairly challenging homework questions, and it does pretty well. And this is where I say AI capability has improved to a point where where the kind of the response it gives is A level response. And actually, this is using it's called the COA Physics GPT because I'm actually using a custom GPT that I started putting together for my classes. And I'll show more about that in a bit. So that's actually this semester. So if you are looking for me just testing out ChatGPT, you'll have to go to earlier semester. Oh, and yeah, this is drawing free body diagram. This is ChatGPT 5 is the first model where I was seeing, oh yeah, this is a passable free body diagram every now and then. Sometimes it doesn't do it quite right. Yeah, problem solving with the ChatGPT 03 last semester. This is when a lot of these sessions I'll start out with basically what I think is an improper use of generative AI. Kind of just paste in the question and let's see, need help. Oh wait, did I stop doing that? So yeah, some of the sessions I'll have. Let me see if I can go a little bit earlier in the semester. So a little bit earlier in the semester when I'm still kind of trying to show two sides of generative AI. The dark side where you might say this particular way of using AI is not helpful to your learning. Just basically ask it a question and it'll just answer it because unless you tell it that you are trying to learn, it'll just it's a people pleaser, so it'll default to just answering. And if you want to learn from generative AI, you have to tell it kind of help me understand, help me learn, explain things, don't give me the answers right away. This is something that I still do with my calculus-based physics class, and I'll think of a way to do something similar for this class, conceptual physics, physics 10, and I think this is kind of a way in which AI can be really useful for your learning. And finally, one last way in which I still use AI, continue to track its capability and progress is I do a timed assessment demo, and we'll have some timed assessment for this class as well. So the timed assessment demo, I can show you the most recent one I did for Physics 4B. It's gonna be at the very end of this playlist. I posted it not that long ago. So when I do these timed assessment demos, I do it twice. I first cheat with ChatGPT, and I do mean cheating, like no joking. The first half of what I do here, it's not something any student should do. It's a violation of honor code. It's a violation of the timed assessment rule. But I want to. Some of these rules were actually like time limits. They were originally an anti-check measure that I implemented because it worked against the check. It doesn't work against the ChatGPT anymore, and it's ChatGPT is pretty capable thing that can answer these multiple choice questions fairly accurately and pretty quickly. So I do it under 10-minute time limit, but in these demos I can usually do it 3 to 4 minutes. Me copying and pasting the question into ChatGPT responding, and let me see what kind of result I got. I think here I got maybe 90%. Let's check. Oh wait, I think we are already past. Let's see. I'm trying to find where. Yeah, ChatGPT got 90%, and I do this as a kind of friendly competition, where I'm gonna repeat the same thing, but trying to beat ChatGPT both on accuracy and time. And so far, I've been keeping up. I think I might have lost on time once or twice. Maybe tied, or I don't think I ever lost on accuracy. But this is the kind of thing. But this is another way in which I keep track. So the multiple choice questions for this class being easier, ChatGPT is probably going to do pretty well. It wouldn't surprise me if it regularly gets 100% on the kind of the questions you will see on your multiple choice timed assessment. So this is a way in which I've been kind of keeping track of, keeping tabs on, keeping on the cutting edge of what the generative AI looks like, so that as your instructor, I have a good sense of what kind of technological tools are available to you. And I will also say that I use ChatGPT in my work. There are certain tasks that I realized I could do a lot more quickly and possibly even better with the ChatGPT. So I will show you my ChatGPT account that I pay for and show you some of the ways in which I've been using it. You know, some of these are those what I do in virtual class sessions. And some of these, which don't make it into virtual class session, are things like, so you know, this video is being recorded to be part of what I'm going to be calling Physics 10 in 30 lectures. And I've done something similar for Physics 4A, 4B, 4C. And for some of the additional work I'm doing with that, I needed to clean up the transcript of these lecture videos that were auto-generated by YouTube. I kind of need to do that for ADA reasons anyway. Auto-generated captions are not ADA compliant. And originally I was doing that by hand. That's I think what you see. So yeah, before lecture 3, lectures 1 and 2, I was cleaning those up by hand, and it was taking me the entire day, like 8-hour work day, to process one lecture video. And I thought, ChatGPT is pretty intuitive. As in, I could give it a pretty flawed transcripts and just the transcript. Like this is the YouTube's auto-generated transcript. No punctuation, lots of typos, mistakes. But it's the kind of thing I think as I was processing it manually, I realized correcting a lot of this, you don't need the audio. Like someone who's aware of the physics content can actually correct this just looking at the text. So I tried testing it out with the ChatGPT, you know. Hey, I have these auto-generate transcripts. Can you fix it? And it did it pretty well. Like taking this, generating something that looks like this, and I do a final review, watching the video while comparing against this text, and that really sped up the process for processing lecture transcripts. So I've used the ChatGPT that way. And I've also used the ChatGPT in other ways that you will, I guess, also see in your class. Let me see. So maybe I could do it through here, but I think maybe the better way to demonstrate it is through the final work product. I used it to generate the lecture comprehension questions that you will see. That's tied to these the Physics in 30 lectures series. So this is my Physics 4A class. The MyOpenMath version of it, students don't usually see it, but let me use this to show, for example, the lecture comprehension questions for lecture 1. And this is when I was putting this together. So you know, I've put together the collection of lectures from the recorded lectures that I've had, and the kind of the impetus for doing that was to put it into this MyOpenMath video queued assessment, so that students have more incentive to watch the lectures, and also I have a better way of keeping track of who's watching the lectures and who's not. So the format of this assignment is that there's one long lecture video. That's what all these links go to. And it's video queued. At the end of a particular segment, it drops you into these questions, asks you these questions. And then when you continue video, it plays the video, that's this. And then after that section finishes playing, it drops into these questions. And putting together these questions, When I was doing this, I didn't have a lot of time. Like I was kind of building the boat as I was trying to float in it, and I thought. So with all this, what I really care about is the fact that you would hopefully watch the lecture videos. The kind of the questions themselves, I didn't care as much, and I thought, hey, here's a work product whose real quality I don't care about. I care that you are incentivized into watching the lectures. I don't care like if these are the best multiple choice question about the lectures. So I thought, hey, let me use AI to generate these questions, and I review them, make sure it actually matches up to the lectures, and I'll probably do something similar for your class, and I might actually modify some of these. I've been thinking about it. I think I want to introduce a new question type where it's it asks you to kind of recall a lecture quote, lecture snippet. But I do fully expect I'll be using AI when I generate these questions, because it's done okay with the physics 4A, 4B, and 4C, and if I don't see a reason not to use it. And I will be, again, as I'm telling you now, I'll be upfront about it. I use AI to generate those questions, and they are based on my non-AI generated lecture videos. So I think I don't think I've cut any corners when I do this. And finally, this is more of a kind of what I think I will do than something that I have done. So, the Google Nano Banana most recent release, it was really impressive. I saw a demonstration of someone kind of writing a math questions at the top, and then just having a prompt, solve this question in the style of this handwriting in the same color pen, and it did it really beautifully. And a friend of mine talked about how he uses a Notebook LM, the Google AI product, and I started looking into it, and I think I might use it. And I don't know the exact format in which I'll use it. So, within my Google account, this is actually used to be my free Google account. I had to start paying for it so that I get this Notebook LM features that are the pro features. I started playing with the physics 4A and 4B. These classes have the advantage of being, I have a full set of lecture transcripts. For this class right now, I don't have a full set of lecture transcripts. I don't have a full set of lectures. What we do have is the textbook. So into the sources, I put in the textbook. I put in the course module structure so that the AI knows how the textbook fits into the course structure. And actually, you have seen, if you are watching the lectures in order, you have seen one output of this. For the chapter 0 overview, I generated this mind map that's based on chapter 0 alone and the table of contents. And I used this as I was recording the chapter 0 overview video. And I think you've seen the edited version of that. And so one thing that I am hoping to do is share this link with the whole class. And I think a guest who has access to that link, you have access to the chat and the sources. You can kind of chat about the sources here. I don't think you have capability to generate new assets in Studio. And I might put together a kind of discussion forum where you send me the request for any new assets you want me to generate. Maybe the ones that are here are not enough. You want something new, then, okay, tell me what kind of prompt you want me to use in generating the assets, and I'll do that. So this is more of a future-looking thing. I haven't used this in my past classes yet, but I'm actually excited about it, how this might come together. So again, I use AI in my work in teaching, and I think many of you in your professional work, you might be expected to use AI the same way a lot of us are used to using word processor, spreadsheet, computers in your work. So, with all this talk of AI, I think this is the important question for you. Should you use AI, and how should you use AI, assuming you use it? And let me start out with this maybe in case I don't know, maybe you are that student who has who looked at AI, saw the AI hallucination, and thought, oh, this isn't for me. I'm not gonna deal with it. In certain aspects of what I do, that is for me too. Like tried using Gemini to write a email response, and I didn't like it. I have a particular writing style, writing voice, and AI sounded nothing like me, and so I won't use AI to write personal correspondence. And I also will never use AI to grade your work. Any of your work that's too tedious for me to grade by hand, I'll find a way to automate the grading that doesn't use AI. So any grading feedback you get from me, you have guarantee from me that that will not be AI generated. Sometimes I do copy and paste the templates, but the original version I wrote it myself. And so if you're that kind of student who looked at AI and thought, this isn't for me, I don't want to use it, then I have a good news for you. Nothing in this class requires you to use AI. So if you are saying no to AI, then great. You and I will get along fine. You'll have a great time in this class, hopefully, and you don't have to use AI. I do think generative AI, unlike Check, the cheating website, AI actually has a potential to assist in your learning. So if you have been using AI and you think you will want to use AI in this class, that's also fine. I think there's great potential for AI to improve your learning experience, and I don't think it benefits anyone to somehow, starve us from that resource. It's like, I would never require you to go through this class caffeine free. Like caffeine is a performance enhancing drug, but it's legal. I use it. I'm drinking tea right now. There are kind of the things that will help you do things better. That's perfectly fine to use. And what I would say should be your guiding principle for whether you are using AI the correct way should be if we are using it to learn. So, however you might be using AI, if you are using it to learn physics, then great. That's the way in which I want you to use AI if you use it. And so let me share the grading standard I use for my Physics 4A this semester, fall 2025. And so I haven't taught Physics 10 in a while, so I need to start putting together the material. I'll have a version of this language in your syllabus, and you can expect to see similar grading standards. So in the Physics 4A syllabus, you see here, these are the grading standards. For A, excellent understanding. And there's this qualitative description that describes an A student. And B, good understanding. And again, there's this qualitative description. And C is where, I can say, all right, you don't really understand the course content, but you put in the enough efforts, so you deserve to pass. So when you look at the standards for B and A, that's where you will see it's based on your understanding. And it's basically based on a skills demonstration. Are you able to answer homework questions? Are you able to solve problems? And the way these standards are enforced in my Physics 4A, I do a required in-person one-on-one meeting. Our Physics 10 is a 100% online class, so I'll need to think through logistics in which you will be able to demonstrate what you have learned in class. And when I to finish deciding on those logistical details. What I can tell you is that it'll be based on skills demonstration. And one thing that AI definitely has changed, both for those of you who use AI and who don't use AI, is that it certainly has devalued the value of written work itself. You know, the written work that you might be submitting that I didn't see you complete. The level of quality at which AI can generate those. When I see written work, I kind of go in with the assumption, yeah, that might be AI generated or it might be AI assisted. And what I would say is, if you have AI assistance in many of those written work, homework, as long as it's not timed assessment, that in and itself might be okay. Ultimately, what the measuring stick for was it okay, was it not okay, is what you learned in the process of creating that written work. Whether you had AI help or not, if you learned something that you retained while you are producing that written work, then great, that's what I want you to do. And however you did it, even if you didn't use AI, maybe you had a friend help you, or you crammed in a way that, you know, things went through one ear and not the other ear, or I guess came in through one eye, went out the other. You didn't retain any of the information, then you know, that written work doesn't represent your understanding. So that's what I want you to focus on as you go through this class, and potentially use AI to help you learn. I want you to focus on what you learned, because ultimately that's what you will be judged, graded on. Your course letter grade, A's and B's especially, those will be assigned based on, did you understand the physics? And our class is a conceptual physics class, so the kind of the physics problem solving is not as quantitative, math oriented as physics 4A would be, but still I want you to focus on what kind of physics explanations can you give in that some sort of one-on-one meeting. And again, as you are doing this work, if you are using AI, that itself I think is okay. I think of AI like a training wheel when you are learning to ride a bicycle. And the point of the training wheel is to be able to ride the bicycle without the training wheel. If you rely on those training wheels so much that you can never ride a bicycle without those training wheels, then you're not learning to ride a bicycle. You're just leaning on those training wheels. And if AI's kind of interaction with AI is helping you absorb content, helping you kind of summarize, helping you focus on the important salient aspects of the course material, then great. By all means, use it. But if the way in which you are using AI leads you in a place where you can never answer physics questions without using AI, then you haven't learned anything, and the grade you get will kind of reflect the fact that you never came off the training wheel. So yeah, I think that's everything I want you to say about generative AI and learning physics in this new brave new world in which a lot of work that only human beings could do even 5 years ago, now computer can do. And I am excited to see how it improves. So, you know, some of these resources that I generated, they are, you know, some of those are not quite relevant, but I can imagine either through better models or through better prompting or arrangement of things, this can be a lot better. It's like, I keep thinking of Star Trek, you know, the way in which computers are in Star Trek, that's finally becoming a reality with these AI tools. And I am excited about the future. And I do believe in human supremacy. These generative AI. I almost said a slur that starts with C and ends with have a k sound in it. Not gonna say that in case, you know, there's a robot uprising in the future. But we human beings, we have image of God. These artificial intelligence, they don't. Ultimately, what matters are human beings and human progress. What matters is what you learn. And if these robotic tools are helping you do that better, then great, use it. But the future is for us human beings, not AI. AI serves the intent and the benefit of humankind, not the other way around.